Okay there, Pythonistas. It's nighttime here now, and the wind is howling outside. I'm kind of in a warm house, and I'm grateful for that. The news tonight, it came from Alabama, and it was all about the tornadoes. And, it's a harsh planet, and we're lucky to live in a time when technology has helped us so much, but we hope that we will continue to develop even better technologies to help us even more. There's reason to hope. Anyway, speaking of technology, I'm back at Spider here, as you can tell, and I'm rounding out a series of 3 YouTubes where I've been sort of introducing a couple things. Number one, the syntax, how Python is put together so that you can do the normal arithmetic calculations that you would expect from, say, a calculator or whatever. And I've been showing off how today in a modern Python, you're able to use Unicode characters. You're not limited to what we used to call, or still call, ASCII, nor to just what we used to call and still call Latin 1. You can get into the Greek alphabet. You can use Chinese characters. Now, when is it advisable to pepper your programs with non-standard, from the point of view of contemporary programming, still quite non-standard symbols? Well, it depends on what you're trying to accomplish. I'm working in the world of the golden mean, and to me, it's an important enough um, number that I'm willing to sort of give it special treatment by giving it a Greek letter. But you'll notice a lot of the theme here, what we're talking about in these 3 videos, is how far can we go towards traditional, conventional mathematical typographies? Because I think a lot of what stands as a cultural sort of wall or divider between the mathematical community and the computer community is simply that computer languages can't give us like giant letter sigmas and all the Greek letters and so on. And we're just not as expressive in terms of typography. But that changed a lot with Mathematica and MathCAD and Maple, and nowadays we have computer algebra systems, and we can use something very close to conventional typography, but not in Python, and it tends to be an expensive thing to do. So what I'm going to do nevertheless is cut and paste this material to a Jupyter notebook, which I have ready for our fun. Since I just jumped here, I'm gonna restart the kernel and clear the output. And I'm gonna start right in with a sigma expression, not an executable expression, but you can see there's our fun little Greek letters and our giant sigma. And in this sense, the computer world has solved the need for mathematical typography, which are always going to show up in articles and so forth. We have this language called LaTeX, thanks to Donald Knuth, who gave it to us, for typesetting, type formatting, mathematical equations. And I'm no master of LaTeX. When it comes time for me to figure it out, I jump to web pages and look things up and just learn a little bit what I need to learn on the fly. Whereas if you're a grad student in, say, mathematics or something, chances are you're going to have a much deeper knowledge of LaTeX than I do. You'll write entire papers, perhaps, in LaTeX, what a physicist might do. The table of contents, the index, LaTeX is more than just about making equations. You can do entire books this way. So I have high respect for those kind of capabilities, and using Jupyter Notebooks, you can start to scratch the surface and teach yourself some of the basics. That's what's so useful about these technologies, is they are gradually widening your horizons in many directions that you may not suspect or know about. So I just run a code cell in a Jupyter Notebook by doing Shift Enter, and I guess it ran a second ago already. Let's start again. Let's do restart, clear output, and start with an empty Jupyter notebook in the sense that the code cells are not yet run. So I'm waiting for this 2 over here to turn to blank. There, now it is. So I'm going to import Gimpy 2 this time, which I didn't before in the previous video. I said I could do that, but I'm leaving it till now to actually do it. And then we get to set what precision we want to compute at. And this 200 is 200 bits of precision, which means that's how many bits of memory will be allocated to one number. And this is something you can adjust. I could easily go to 300 or 400 bits and so forth. So it's up to you to set your precision. And then I use essentially all the same code as before. I enhanced it a little bit with some labels. That should actually be sequence 1. I'm going to change the code right in front of you there. And then we go through my creating of the different expressions and then evaluate them as before to see that, yes, we still have these phi identities where you've got Fibonacci number coefficients and exponents that are dropping by 1 each row but a little bit offset from each other. Likewise, the Fibonacci coefficients, you can see them vertically in the 2 columns, are a little bit offset from each other. But now I have a nice 18 points of precision, 18 places after the decimal on each one because I'm no longer using floating point. By the way, what's going on here, and I didn't explain before, if you're kind of new to Python, what's this double star in front of args? What is that about? That has nothing to do with exponentiation. That's all about dictionary stuff. So args is a dictionary. I create it as an empty dictionary, and then I start giving it keys with arguments. So I'm setting up an equation, basically, one of these strings. I'm going to be substituting the arguments, the dictionary arguments, into a string to get each one of these expressions. So these are key values that I'm creating. That's what a dictionary is. It's just a set of key value pairs. And A, B, coef0, coef1, those are the keys to this dictionary, and you see how they appear in my placeholders up above. So we're extracting into an expression, a string, by name, various missing contents. In other words, we're filling in the blanks. Every time you see curved or curly parentheses, I should say, in this quoted string, what you're looking at there is a placeholder. And what you're seeing inside the curly braces to the left of the colon every time is what's going to serve as sort of the hook that's going to reach in by name into this dictionary and pull out the corresponding value. So it's going to reach in and grab an A, it's going to reach in and grab coef1, and those are what we're setting every time we go around the loop because they keep changing. Fibonacci numbers change, the exponents change. And then we do this double star in front of the dictionary to sort of explode it out into named arguments. Because what dot format, the format method of the string type is looking for are actually just like when you call things with named arguments, that's like saying A equals 3, B equals 10, and the order doesn't actually matter. It just matters that there's equal signs there. The actual equal sign. That's what we call a named argument or keyword argument, is when you have name equals value, name equals value. And a dictionary is being key value pairs is just a hair's breadth away from being the correct format. It's just a dictionary is a single object. It is not a set of named arguments. So to fix that, to explode, as we say, a dictionary into named arguments, that's when we put the double star in front. So that's been going along even since the previous video. I just described it now. And then here is our sequence function that's just going to verify the LaTeX that we had up above, higher up. It's going to prove to our satisfaction that even in the corner case, when we're saying n equals 0, so back up to our sigma expression, when n equals 0, then I is 0, and then it stops because n is 0. Otherwise, we count up to n. N is some positive number greater than 0. At minimum, n is 0. In that case, 0 plus 1 is 1, times 2 is 2. And when we do the sum on the right, the left term is just going to be 0 because the 0th Fibonacci number is 0. And on the right here, we're going to get 2 as our coefficient, and phi to the 0 is just 1. So 2 equals 2. So the corner case is correct. And then when we go 1, 2, 3, in other words, make n bigger, it's just going to keep giving us another 2. In other words, 2, 4, 6, 8, up to 20. 2, 4, 6, 8. And these are just, again, these are the extended precision numbers that we expect because we're doing all our computations now not with just plain old floating point numbers, but with extended precision numbers imported from GMPY2. So that's Jupyter Notebooks. Very typical workflow. Start with something in Spyder, do some development, figure out the nuts and bolts, and then develop from there, kind of as your scratch pad, a more formal Jupyter Notebook presentation that's more meant for a wider readership, where you can put in lots of additional explanation, do what we call literate programming. All right, that was fun, and see you next time.